So good evening. Today we will be starting with systems. Okay. So in our previous lectures we have already discussed what is a system. It is nothing but a mathematical model. Okay. So a system is a mathematical model of a physical process that can relate the input with the output of the signal. Okay. So what we will do, we will be taking a very common example of a system. Say for example, most of you might be knowing about the non-inverting amplifier. Okay. So what is the non-inverting amplifier? All of you must have studied about this non-inverting amplifier in your analog electronics class, right? So we have V in, V out, then this is RF, this is R1, right? So we all know that V0 is given by 1 plus R2 by R1 into V. Okay. Now we can take this Vi on the other side and we can say that A, which is regarded as the gain of the circuit, it is equal to V0 by Vin, which is equal to 1 plus R2 by R1. Okay. Now if you see, this is a mathematical model, right? 1 plus R2 by R1, it is basically a mathematical model which helps us in connecting the input with that of the output. So basically if you see, your V0 is directly proportional to the Vin. Am I right? V0 is directly proportional to the Vin, and if we apply this mathematical model which is given by A over here, then we get V0 equals to A into Vin, right? Now, in this case, if you see, we are having only resistances. We are having only resistances, right? So, resistance is regarded as a memoryless component. Okay, that means it does not have memory. It does not depend on the past inputs. Okay, it does not depends on the past inputs as in the case of capacitors. Capacitors, they their output at the voltage drop across the capacitor, it is dependent on the past inputs to the capacitors. Okay, but in this case it is not the case. Resistance will not have any memory. That means it will not have any, it will not give you an output which is dependent on the past inputs. Okay, unlike in the case of capacitors and also in the case of inductors, right? So since this is a memoryless system, so we are talking it as a, or we are giving the notation of gain A. Okay, so if I if I want to generalize this equation, then this A term, it is given by capital T, which is regarded as the transfer function of a system. Okay, so transfer function of a system is nothing but, and it is a mathematical equation which will help you to get the output of the system by performing some mathematical operation onto the input. Okay, so if you consider this one, I can have this RF completely eliminated and I can just change it with the capacitor C or even an inductor. So in that case, this RF, it may become either XC or XL. Okay, inductance. You tell me. I have given you the. I have made you understand what is happening. So can you tell me the definition? What is T? Who can tell me the definition? Voltage gain. It is in. You can talk about it when you're using only the resistive thing, resistive components, right? Because it will not have any memories. When we talk about these transfer functions, it encompasses all the components. It may be a memoryless system, it may be a system with memory. So it is a more generalized term. Okay. So transfer function, it is a mathematical operator which gives you a relationship between the input and the output. Okay. So the output will be basically you will be getting the output wherein the mathematical operator it is being applied onto the input to get the output, right? Then only you are getting the output basically. Yeah. So that is the output, right? So this is the transfer function. So in general we call it as T. So if you see, we give an input and we get an output. Now in this case, if you see, we are having only a single input and single output. So it is regarded as single input, single output system. Okay, it is getting one input and it is giving you one output, and hence it is regarded as single input, single output system. In the case of in the second case, if you look over here, so what kind of system it is? You are having multiple inputs, multiple input, multiple output systems. Can you give an example of either of this? In the first case, if you place a thermistor on the surface of our body, what it will do? It will collect the temperature information from the surface of the body and it will give you the temperature readings. Okay, so it would be a single input, single output system. On the other hand, when we talk about multiple input, multiple output systems, you must have seen in the TVs when the patients are being admitted into the ICUs and all these things, you will be finding a whole lot of sensors put on to the body of the patient. Say for example, you will be having the ECG sensor, you may be having the pulse oximeter sensor, okay, you may be having the respiratory sensor. So you see, you are getting multiple inputs into the system, and the bedside monitor, that is the monitor which is giving you the outputs like what is the heart rate, how the ECG is being performed, what is the ECG graph. Okay, and there is a monitor which will give you a combination of all these outputs. So all the outputs are being displayed. Okay, so multiple input, multiple output system. Okay, so herein we are having multiple input, multiple output system. So these are uh, one of the examples of single input, single output, and multiple input, multiple output thing. Okay. The same thing over here. I have again coming back to this non-inverting amplifier. If you talk about the inverting amplifier, the same thing goes. In the inverting amplifier, A is given by A is equals to minus of R2 by R1, where R2 is the feedback resistance, right? Again, see, it is a mathematical operation. Okay, what does this negative sign implies over here? What does this negative sign implies over there? Here, say for example, both RF and R1 both are equal. RF is equal to R1. Okay, so this gets cancels out and we get A equals to minus 1. So what does this signify? What does this negative sign signifies? So if you are having sinusoidal signal like this, then what would this signify? This would signify that there is a negative unity gain, so you will be getting a mirror signal. So positive will become negative and vice versa. Okay. In the case of if it is say if A is equal to 2 in the case of say non-inverting amplifier, so what will be having, you will be having the same signal what you have given, it will be having an amplitude of 2 and it will be in phase, whereas negative means it will be 90-degree out of phase, right? Because it is opposite to each other. Okay. So there is a what you call voltage inversion. Now coming to the classification of the systems, there are several categorizations of the systems. The first one is the continuous time and discrete time system, systems with memory and without memory, causal non-causal systems, linear systems and non-linear systems, time invariant and time varying systems, linear time invariant systems, stable systems and feedback systems. Okay. Now what happens in continuous time and discrete time systems? If the system is capable of handling continuous time signals, then they are regarded as continuous time signals, and if the signals are capable of handling discrete time signals, they are regarded as discrete time system. So what happens for the analog systems? What kind of system it would be? Analog, how many of you are telling continuous? Only 2, 3. And the rest, what do you say? Rest says discrete. And what is the definition of analog I told you in the last class? Yeah. It may be in continuous time, it may be discrete time. Right? So depending upon, so what is the definition? Definition is it will be having infinite number of amplitudes. And since it will be having infinite number of amplitudes, depending upon the nature, whether it is continuous time or it is a discrete time, you can either use the analog signal either in the continuous time system or in the discrete time system. And what about the digital systems, digital signals? They are discrete, they could be processed in the discrete time systems. The reason being, they are already discretized. Digitalization happens after the discretization has happened. Okay, so after the sampling and followed by quantization has happened, then only it becomes a discrete time signal. Okay. Now coming to the systems with memory and without memory, I already told you if you are having systems which are resistive in nature, they would be without memory, and if you are having capacitance and inductances, they would be systems with memory. Then causal and non-causal systems. So what are causal and non-causal systems? So if you see, a system is called causal if its output yt at any arbitrary time t equals to t0 depends only on the input xt for t less than equal to t0. Okay, that is the output of a causal system at the present time depends on only the present or past values. Okay, this is the important thing, present or the past values of the input and not on the future values. Okay, so we are given over here two types of systems, yt equals to x of t plus 1 and the next one is yn equals to x of minus n. Now let's see how do you find out whether it is causal or it is non-causal. Okay, so in the first case, this one, let us check it. So say for example I want to find out y of 0 is equal to x of 0 plus 1, so it is 1, so it is the future value. Okay, it is the future value. If you remember this, it will be n or t and amplitude. So if you are at 0, your right hand side values, they are the future values or future input values. Okay, Similarly, let us take the other cases. Whenever we want to find out the causality of the system, please be reminded that we need to check it at three instances. One at the negative instance, one at time equals to 0, and the third one at time in the positive half. Okay, so let's check for y of minus 1. Y of minus 1 is equal to x of minus 1 plus 1 0. Again, with respect to this y value, this is a future term, x0 is the future one. Okay, and also let's see y1 equals to x of 2. Again, with respect to 1, it is the future value. Okay, so in this case, what is it? It is a non-causal system. It is a non-causal system. Okay, now let us take the next example. This yn equals to x of minus of n. So y0 equals to x0. What does this indicate? This is a causal system. Okay, then y of 1 equals to x of minus 1. So what should be the system be like? What should be the system be like? Causal system. What I said, you have to check it in at three instances. What you will be getting? So what does this indicate? So the thing is that only if in all the three cases the system is causal, then only you can say that the system is causal. If it is non-causal, you cannot, even in one of the instances, then you cannot say that it is a causal system. Even if in at one time instance, if the system is non-causal, that means the system is non-causal. Okay. So this one we already discussed. This one also we discussed, right? Now coming to the linear systems and non-linear systems. What do you mean by linear systems and non-linear systems? A linear system would follow the rule of additivity and homogeneity. Okay. What does it say? We considered one amplifier, non-inverting amplifier, and we saw that it is having a gain of 2. We considered that one, right? Let us consider the same thing and move forward. We are talking about a non-inverting amplifier. Say for example, I am having x1. Okay, x1 is equal to say 2. Say for example, I can also take 1. Okay, so x1 is equal to 2, and this, when x1 is equal to 2, my y1 it will be equals to, how come? 2 multiplied by 2? 4. Okay. Secondly, x2 equals to whatever you say, 1. Say for example, here. So y2 would be 2. Now, what we have to check is that when we add up these two values, x1 plus x2, what is the input value? 3. And this would give me, say for example, I call it as x dash equals to, so I will get an y dash equals to 3 multiplied by 2, 6. Okay. Now, what happens if I add up these two values? Say for example, double dash. So it is again 6. Okay. So this y dash is equal to y double dash. When you get this kind of scenario, then the system is following the rule of additivity. Rule of additivity. Linearity अभी बहुत दूर है. Okay. In the first case, y dash we got when we have added up the inputs. X1 plus x2 is being put in, that multiplied by the gain, that is y dash. Okay. In the second case, we are adding up the output values. Okay, we are adding up the output values. So that is what it is saying. Transfer function of x1 plus x2. This x1 plus x2 is the independent addition. Okay, x1 plus x2 is the independent addition of the inputs. So independent addition of the inputs, then we are having this transfer function operator that will be giving us the output which is equals to the addition of the outputs due to x1 and x2. Are you getting my point? This is clear. Similarly, now take this case ax. Let us take the x1 only. X1 equals to 2. So this will give you y1 equals to 4, because this is the scaling factor. Homogeneity, it is also regarded as the scaling. Scaling means multiplication. 2 multiplied by gain of 2, it is equal to 4. Okay. So if you see over here, what has happened when in the next case, if I say x of 2, what is happening? Say I am multiplying this x2 as 2 into x1, which is equal to 4. Okay, what will be my y2? Will be 8, right? It is 8. And what will be my, so we can call it, if you want to compare it with the previous one, we can call it as y dash. Okay, and when you, and what you call for the second thing, y double dash, which is due to the output, due to the scaling of the output. Output is 4, alpha over here is our 2, so 4 to the 8, right? So in y here also, if you see, y dash is equal to y of double dash. Y dash is equal to y of double dash. So it is also following the rule of homogeneity or scaling. So a linear system, it will follow both the rules, additivity and homogeneity. Okay. Next comes, when we combine these two, we get the superimposition property. What it says, if you see, the input is being first multiplied, both the cases, alpha 1 x1 plus alpha 2 x2, which is equal to alpha 1 y1 plus alpha 2 y2. These are similar. So what we have done, we have basically multiplied, in this case if you look over here, we have multiplied x1 with alpha 1, x2 with alpha 2, and accordingly we have got alpha y1 plus alpha y2, alpha 2 y2. Okay, because of the scaling property. If we are multiplying or scaling x1 with a factor, our output will also be scaled by the same factor. Similarly, if we scale the second input signal, our output signal will also be scaled by the same amount. Okay. So when we combine these two, we get this superimposition property. Okay. So if your system it follows this additivity or homogeneity, then we call it as linear system. Okay. Now in many of the cases, while we do solve the problem, we consider alpha 1 equals to alpha 2 equals to 1 to make our life simple. Okay, that means we are basically looking into the additivity and we are considering that if a system it follows the additivity rule, it will also follow the homogeneity rule. Okay, so we are assuming, okay, for doing the numericals most of the cases. So let us take look into some examples. So if you see yt equals to t into x of t. So this is the signal. So x of t will be representing with say x1 and y of t will be representing with y1. Okay. So for x1 we are getting y1, okay, which is equal to t into x1. This is for the input x1. For the input x1 we are getting y1 equals to t into x1. Similarly, for x of 2, we are getting y2 which is equal to t of x of 2, x2. In the third case, in the third step, what we will be doing? We will be adding up y1 plus y2 to get y dash. Okay. So when we are doing that, we get t gets common and then we get x1 plus x2. In the case of y double dash, when we are adding up the inputs, we get t of input is x, so x1 plus x2 when input is being added. Okay. In the first case, we have added the outputs, addition of outputs. In the second case, we are having addition of inputs. You can do in the other way also. Yeah, you can perform this addition of inputs first and then solve this. The main thing is that you have to show both the steps. Okay. So since addition, the outputs due to the addition of the outputs and the output due to the addition of the inputs both the same, then hence this system is regarded as linear system. Okay. Similarly, let us take up this example yt equals to x of t plus 1, which we looked into previously. Over here, y1 equals to x1 t plus 1, y2 x2 t plus 2. Okay. Y dash, which is basically the addition of y1 plus y2, it is equal to x1 t plus 1 plus x2 t plus 1. Okay. Then y double dash, nothing but we have x1 t plus 1 plus x2 t plus 1. These are the inputs. So both of these are equal. Hence we can say that this system is a linear system. Okay. Then look into this example, second and third. These are very important. Students do mistake over here. Okay. Yt equals to x square t. Okay. So t is independent. Please be reminded over here. T is independent over here. So basically we can say this is x of x square basically. Okay. So it is x square. So due to x1 we will be getting y1 equals to x1 square. For x2 we will be getting x2 square. Y dash we are having x1 square plus x2 square. Okay. Then y double dash is x of whole square. What is the input? Input is the x. So what is changing? Input is changing. x1 plus x2 is changing. So input is changing to x1 plus x2 whole square. Are you getting my point? Here input is x and we are having power to that. So when we are in the A and B, we are changing the input x1, output is x1 square. When we are having x2, output is x2 square. Okay, but when we are coming for this change in output, when there is an addition of inputs, okay, so this x is replaced by x1 plus x2. Okay, so x1 plus x2 whole square. So you see, C and D, they are not equal, and hence it is a non-linear system. Hence it is a non-linear system. In the second case, it becomes interesting if you see y of t equals to x of t square. X of t square. So t is the independent variable. T square is the independent variable. In this case, t was the independent variable. Here it is t square. So x is a function of t square. Okay, here x was a function of t. So here the x is input is function of t square. So when we are having x1, we are getting x1 t square. When we are getting x2, we are getting x of t square. And when we are getting this y dash, it is x1 t square plus x2 t square for this one. Okay. In the last case, what is it we are having? The signal is x1 t square plus x2 t square, because our signal is the whole signal. We do not have square onto the signal. We do not have the square onto the signal. Okay. So on the here we are having the square on the independent variable, not on the dependent variable. Okay, not on the dependent variable. Am I clear? So since y dash equal to y double dash, we have this as the linear system. Okay. Now coming to the time invariant and time varying systems. Time invariant means whatever the system you are having, it will give you the same output at all instances of the time. That means if I give an input at this moment, say after 2 hours, it is giving an input of t. Okay. Suppose after 1 hour or 1 minute, you are giving the same input. So after 2 hours from there, it should give you the same output of it. Okay. So a system which gives the same output at whatever time you give the input, that is regarded as the, those systems they are regarded as the time invariant system. Okay. On the other hand, in the case of time varying system, depending upon when you are giving the signal input, your output will be varying. Okay. So your output will be varying. We will take the examples over here to get an understanding what is happening. So say for example, we are having the system yt equals to t multiplied by xt. Okay. In the first case, what we will be doing? We will be delaying the input. We will be delaying the input. Okay. So when we are delaying the input, the first step is the delaying the input. Keep this in mind. Delaying the input. In the first step, you are having delaying the input. So let us represent it by y t comma k. How do you delay? We are trying to delaying the input by k units. T minus of k we have studied. Okay. So t multiplied by x of t minus k. So we are delaying the input. In the next step, you have to change t to t minus k. Okay. Delaying means when t is your independent component. Okay, when t is your independent component. In this case, is the t independent component for your signal? No. But is it? This is your input signal, and herein t is the independent component for the variable x, right? So when we delayed the signal, so the independent component got delayed. Okay, t minus of k. On the other hand, this is not a part of the input signal. It is not a part of the input signal. Okay, in the next case, we are replacing t by t minus k. So we are just replacing, hence this t, it got replaced with t minus k, and this t also it replaced by t minus k. Okay, now these two equations 1 and 2, they are not equal, hence it is a time varying system. Okay, so in the first case you will be delaying the input, in the second step you will be replacing t by t minus k. Okay, wherever you find t or n, you just replace by t minus k or n minus k. It is just the replacement. It is just the replacement. First one is the delaying the signal, second is the replacement. यहाँ पर भी आपको t दिखेगा, वहाँ पे ही वहाँ पे you have to put t minus k, and if it is n, n minus k. ठीक है, किसमें क्यों नहीं करेंगे, यहाँ पे किया है ना हमने. जहां पर भी आपको t दिखे, you have to close your eyes and put t minus k. डिले किया है. In the delay, what is delayed? Signal is delayed. Is it a signal component? It is not a signal component. It is a part of transfer function. It is basically transfer function. So what we said, transfer function y, it is equal to y equals to t into x. So this is not a part of the signal. This small t is not a part of the signal, right? This is not a part of the signal. It is basically a part of the transfer function. So what will be getting delayed? Only where you are having this input x, जहां पर भी x लिखा हुआ होगा उसके अंदर जो टाइम रहेगा that would be delayed only, right? यहाँ पे आपका डिपेंडेंट वेरिएबल नहीं है, those all forms the part of the transfer function. Say for example, if you get over here 2t, 2 is not a part of the signal, it is a part of transfer function t. So in the first step it will not replace it by t minus k, because it is not a signal component. You getting my point? Now second stage, yt equals to x of t plus 5 of ut. Ut step function, unit step function, right? We already discussed. From t equals to 0 to infinity or n equals to 0 to infinity, you will be having this. So x of t plus 5 of u of t. Okay, is it a signal? It is not a signal. What is the signal? Only this is the signal. Okay, only this is the signal. So when we are delaying, see, only in this part we are having t minus k. Over here, no delay. But when we replace t with t minus k, Here it will be replaced, here also it will be replaced. So both 1 and 2, they are not equal, hence it is a time varying signal. Okay. In the next step, what you have, yt equals to x of t square, same equation. Okay. In my last class, I told you, when you are delaying it, whether it is 2t or anything, or t by a, or whatever you are having, so what will be delayed? This is the independent variable. So this independent variable will be delayed. So here t square minus k you are getting, right? When you are delaying the signal, in our signal operation, this thing, in my last class, in the combined operation I showed you, minus 2t minus 2. So in that case, I told you, if it is 2t, then that's 2t is the independent variable and you have to delay it, it will be 2t minus 2. Similarly, if you apply the same analogy, here the independent variable is t square. So delaying would be x of t square minus k. Okay. On the other hand, in the next step, when you are replacing t with t minus k, this t is being replaced. Okay, this t is being replaced. So we get t minus k whole square. You getting my point? Is it clear? You have to look into the independent variable. The independent variable is delayed. If it is t cube, it would have been t cube minus k. If it would have been 2t, it would have been 2t minus k. Okay, in the first step. But in the second step, what you will be having? You will be having, if it is t square, t is being replaced with t minus k, that means t minus k whole square. If it would have been 2t, then it would have been 2 into 2 minus k, that means 2t minus 2k. Right? Clear? So again, the output of the step 1 and step 2, they are not equal, hence it is a time varying system. Okay. Then coming to the next question, yt equals to x squared t. Okay. So in the first case, this is the delaying, so t minus k. Okay. So you can write it as xt whole square. So we are delaying this x of t minus k. So x of t minus k whole square is x square t minus k. Now when you want to replace t with t minus k, again this will become x of t minus k whole square, that means x square t minus k. Okay. So 1 and 2 both are equal, and hence this system is time invariant system. Okay, it is a time invariant system. Now coming to the linear time invariant systems. So what are linear time invariant system? If you see, there are two components, linear and time invariant. Linear and time invariant. So linear means it should follow the rule of superimposition, a combination of additivity and homogeneity. Okay, and it should also be time invariant. If it follows both the things, then we call it linear time invariant systems, and such systems are of importance in biomedical industry. Only LTI systems, they are being used in biomedical industry. That means if you do some addition of the inputs and all these things, your output will also be undergoing similar amount of addition. Okay, and also whenever you use this system, you will be getting the same output. Okay, if it would have been time varying, that means what you will be having, suppose you are measuring your basal ECG signal at this moment, it is giving you a good signal. But at a later time, if you measure the same signal, basal signal, it will give you a skewed up signal, right? If it would have been the time varying system. Okay. Similarly, in the linear system, if it is not, if you are not having this additivity, suppose due to some reason you are trying to adapt to biological signals. Okay. So in one case you are getting good results where there is an additivity property is being followed. Okay. Say for example, I want to measure the temperature from my body at this instance, and then I want to couple it with my ECG signal to combine both the signals, and then what happens is that I want to decouple it at a later stage. Okay. So if I want to decouple it at a later stage, I have to apply some filters to extract the DC component from the ECG component. Okay. So if it is not following the rule of this linearity, then I will not be able to do it. Okay. I will not be able to do it because the signal characteristics will be changing. So this is why we need the linear time invariant systems. Then stable means stability means it should give you same response. Okay. So in the case of this stability, we use a term which is called bounded input, bounded output stability. Okay. Suppose you have designed a system. Okay. Now when you are giving bounded input means you are giving finite input. The system is giving you finite response. Okay. The system is giving you finite response. Now this is called bounded input, bounded output. Okay. Now suppose if you give a system an ever increasing growing signal, or okay, which is growing out of the bounds, and if you look into the system, so what will happen? It will be amplifying, and after some time, even though we say that it is directly proportional to the Vn is directly proportional to the V0, but what will happen? They work within a certain limit. Now if they get saturated, that means suppose any amplifier, they are being operated under a DC voltage. Okay. Dual DC voltage, say for example plus minus 12 volts. Okay. So when you are having this plus minus 12 volts, so under ideal condition, what should be your maximum limit? It will go to the plus 12 volt or minus 12 volt. Okay. So what will happen if you give an ever increasing this input signal which is going out of bounds? Your system response, it will go to either 12 and become constant over there, or it will go to minus 12 and become constant over there. Okay. So why this has happened? This has happened because you have given a signal which itself is going out of bounds. You have not given a bounded signal. Okay. So if we give a bounded input and if we get a bounded output, then it is called Bibo stable system. Okay. It may so happen, right? In case of instability, it may so happen you have designed a system whose inherent characteristics is leading to the saturation of the output. This effect where the output signals goes either to the plus 12 volt or minus 12 volt, it is called saturation effect. So you may have designed a system which, even if you have given the bounded input, it is going to the saturation levels, then it is the problem with the system. Okay. Hence we have to say that when we are giving a bounded input and the system is capable to handle that bounded input signal and it is giving us the readings which are well within the defined limits, then we call it a bounded input, bounded output stable system. Okay. So feedback systems, they are specifically of great importance, and it consists of systems having feedback. In a feedback system, the output signal is feedback and added to the input into the system, as shown in this thing, to gain a yeah, stable output. Okay, so this inverting amplifier, non-inverting amplifier, these all are feedback systems. Because what happens is that if you consider the op-amp, I hope every one of you know, if you are giving V in, V out, V1, V2 is output, and ideally the gain of the op-amp operational amplifiers, it is infinite. Okay, ideally it is infinite. So even a certain change over here in V1 and V2, it can give you a result of infinite. Infinite, it doesn't happen. That means you'll be getting to either positive saturation or the negative saturation. Okay, I hope all of you know from your analog electronic class. Okay, so this open circuit, this open circuit gain and all this thing. Right? If anyone does not know, you can just ask me. I can just get it clarified. So the thing is that to avoid such situations, these inverting amplifiers and non-inverting amplifiers, we apply the feedback loop so that the output of the systems, it remains within the box. Okay, so this is what feedback system is. It takes the feedback either from the input or the output, and it takes into consideration those inputs and the outputs to give you a stable. Okay, so the such system, they are regarded as the feedback. Okay, so with this we